Good afternoon. This video looks at S2 chemical reactions. Shout out to 2.4 who've asked me to make this video. So, the success criteria for section 1, I've split the topic into 3 sections. This particular section is about how do I know a chemical reaction has happened. To be successful here, we have to be able to name the 5 ways a chemical reaction can be identified, give the best way of these different ways to find a chemical reaction has occurred, the differences between chemical and physical changes, convert a sentence or diagram to a word equation using appropriate symbols, and give the correct methods used to test for oxygen, carbon dioxide, and hydrogen. So firstly, when we're doing a chemical reaction, what we're doing is converting reactants into products. There's a few different ways that we can tell that this has happened. So on the left-hand side, we can see some thermometers. So a thermometer would be used to measure the temperature of our solution. So in this case, you can see that in blue, the temperature has gone down, or red, it has gone up. So a change in temperature is one of the ways that we can tell a reaction has happened. A change in colour, so you can see this firework picture, or on the far right, we've got this beautiful yellow colour being produced. So changing colour is one of the ways we can find this. We can have the production of bubbles, also known as effervescence, production of a solid being known as precipitation, and we can also have sound being produced. So with fireworks, for example, we would hear that normal sound. So change in temperature, production of a gas, which is effervescence, production of a solid, which is precipitation, change in colour, and the production of a sound. Often production of a sound being because of the production of a gas. So the best way, and really the kind of defining thing that's happening in a chemical reaction, is that we're turning reactants into products. So it is the production of a new substance in this reaction. We can see underneath in the examples that copper and oxygen are being combined in this word equation to give copper oxide. Or it's not always 2 reactants being combined to make one product. We could have hydrogen peroxide degrading to make water and oxygen. So we can see we've got reactants on the left, and we've got a new product being formed on the right-hand side. How do we know a chemical reaction has happened? So these are some of the issues here. So quite often people struggle to tell the difference between a chemical reaction and just a physical change. So in the top left, we can see we've got molecules which have purple circles and then a blue circle attached. So 2 purples and a blue. These 2 reacting together, and they make the 2 purple circles join together, 2 purple circles join together, and then we have the blue ones here. So we can see, as in before, we have new substance being formed. So we have this kind of diatomic purple, and then the diatomic blue. The alternative to this would be a state change, so moving from solid to liquid, liquid to gas. So when we're looking at whether it's a chemical or a physical reaction, is it just that, for example, you have water and it's gone from being solid water, so water H2O with an S after it, to liquid water, H2O with an L, to gaseous water, H2O with a G. And similarly, if here we have copper oxide as a solid, and we dissolve it and put it into solution, and it becomes aqueous, that isn't really a new product being formed. It has just gone from being solid state to aqueous state. So we've looked a little bit at word equations already. So in this case, it's how to make one of these word equations. So I've left the word equations from the previous questions on the screen, and we'll be able to look at how you might make them. So if you were given the question and you were told to turn this block of text into a word equation, a large amount of copper oxide is produced, so that's our products, when 2 chemicals are combined. The first is a shiny orange metal called copper, and the second is oxygen gas found in air. Quite often they'll give you quite a lot of words, and it is just really to confuse you. We're looking for what the reactants, so the 2 chemicals combined are copper and oxygen. And in this case, with a word equation, we don't need to put these state symbols in that we talked about. So it's just copper plus oxygen gives you copper oxide. And similarly, a word equation might have a big text, and really you can summarize it down to hydrogen peroxide is broken down into water and oxygen. So where it says at the bottom using appropriate symbols, we're talking about having a plus sign rather than just saying and having this lovely straight arrow So it's a single line, and then it's got a head. It doesn't need to be a closed head like this. It can be nice kind of flat line-based head instead. Finally, for this section, we're looking at the correct methods for testing for oxygen, carbon dioxide, and hydrogen gas. So oxygen gas, if we have a beautiful tube of that, nicely bunged, given to us, and we don't know if it's oxygen gas, carbon dioxide, or if it's hydrogen gas, what we can do is we can quickly pull that bung out and put a lit splint into it. So this is a piece of wood that is on fire. If we put that in and it pops, we know that's hydrogen gas. If you put the lit splint in and really, it maybe flames a bit harder, but doesn't make a pop, you can blow that splint out, stick it back in when it's a glowing splint. So here on the right we have a glowing splint, and if it suddenly goes back on fire again, we know that that is oxygen gas. So if you've got a tube with an unknown in it, pop the bung off, try it with a flaming splint, doesn't work, quickly waggle it out, put the glowing splint in. If that is relit, then we have oxygen gas. If neither of these work and you're just filling the tube with smoke, you can put in some lime water, which starts off clear, and it'll become a milky, cloudy colour. So to test for oxygen, it relights the glowing splint, carbon dioxide turns lime water cloudy, and hydrogen gas will burn with a squeaky pop. The second section, how do we speed up a chemical reaction? So we're going to look at the 4 ways that a chemical reaction can have its rate changed. We'll look at examples of fast and slow chemical reactions, and we'll look at how exothermic and endothermic reactions differ. We'll then explain the function of a catalyst and how this differs from just the normal reactants in a chemical reaction. We'll look at the function of enzymes in biology and what catalytic converters do. So there are 4 main ways we can increase the rate of a reaction. But before I talk about that, let's talk about what rate means. We start off with our reactants. So if we go back to the slide we've used a few times before, we have our reactants and we turn those into products. But does that take 1,000 years, or does it happen in 1,000th of a second? So we start off with lots and lots of reactants. And here quite quickly, we're turning the reactants concentration is going down, and the products, which was at 0, is very quickly rising up to a point where the reactants appear not to be decreasing anymore and the products appear not to be being made anymore. We can make this process happen quicker if we increase the concentration, increase the temperature, decrease the particle size. So what we mean is, if this is a block of chalk here, if we squash it from a big block here into the same mass but powdered form, it means that if you imagine acid particles trying to react with the chalk, they can only react with the chalk that's on the very outside. Whereas if you smush it up into very fine powder, it's now possible for the acid molecules to react with all of that chalk that was previously hidden inside the block. So if you make the particles smaller and smaller and smaller, but keep the mass the same, the reaction will happen a lot quicker. So instead of taking this long to get to all the products made, the products would have been made here. But it is important, as I mentioned before, when we increase the temperature or we decrease particle size, we're getting the same amount of product produced at the end, we're just producing it quicker at a higher rate. The interesting thing about concentration is, because concentration is the amount of reactant that you have in that unit of volume, if you increase concentration, you do actually end up with more product often being formed at the end. And something out with this particular part of the course, though. A catalyst, so we'll talk a little bit more about catalysts in a second, but a catalyst is something that increases the rate of the reaction. So if you add a catalyst, increase concentration, increase temperature, decrease particle size, add a catalyst. So looking at the rate of reaction, there are some reactions that very briefly are quite slow. So fossilization, when things die millions of years ago and they go underneath the soil, they're compressed, and a chemical reaction takes place where biological compounds are replaced with other compounds. That takes millions of years. Grass growing is relatively quicker, it has a faster rate, but it still takes days and days and days for a few centimeters of growth. Whereas an explosion, or like lighting something on fire, combustion, that is a relatively quick reaction. So fossilization and grass growth are slow, whereas an explosion is quite fast. So another term that we're expected to know is at the bottom, exothermic and endothermic. Very simply, an exothermic reaction is one where, if you take the temperature of all of the reactants before the reaction occurs, you combine them together. Following the reaction, the temperature will be higher, so they've given out energy in the form of heat. Whereas if you take the temperature of the reactants before, let's say it's 20 degrees for both, and you react them together, and the temperature has dropped, the reactant molecules have taken in the energy in the form of heat and converted it into chemical energy. That's been stored in some form of energy, and that means that the reaction solution in the environment has gone down in temperature. So catalysts are really interesting. I quite like this image on the left. So it shows that if your catalyst is this thing in the middle, it is converting this molecule into that molecule, and it's doing it without really taking an active part in the reaction. So catalysts do not get used up. If you put 1 gram of catalyst in at the start, you will get 1 gram of catalyst out at the other side. So catalysts are very important in speeding up reactions. We'll talk a little bit in a second about the biological catalysts, enzymes. But what catalysts do is, if you needed, without a catalyst, to run a reaction at, let's say, 400 degrees Celsius, with the benefit of a catalyst, you might be able to run it at 20 degrees Celsius, room temperature. So what it does is it reduces the amount of energy required to start that reaction. It reduces the temperature, usually, that you can do that reaction at. So they don't get used up at the reaction, they speed them up, and they reduce the amount of energy that is required to start that reaction. So you can run it at a much lower temperature. An example of catalysts would be within biology, we have enzymes. So enzymes are biological catalysts. They're made of proteins in your cells. Some examples of 5 ones here: amylase turns carbohydrates, like, for example, starch into maltose. Lipase, fats are made into fatty acids. Pepsin will turn proteins into peptides and amino acids. Trypsins will break proteins down into amino acids, and lactase will break that lactose sugar down as well. So these are reactions that happen in the body that enzymes make a lot quicker. So what you need to know for the course is that enzymes are biological catalysts, and they speed up reactions inside living organisms. A catalytic converter is our second example. I think this is the last slide within this little bit of the topic. So what catalytic converters do, and what you need to know, is that they take gases that are potentially toxic and greenhouse ones that are bad for our environment, and they convert them into less harmful gases. So it's taking toxic or poisonous gases and converting them into another form that's less toxic. Okay, so our third and last section is our experimental designy bit. So it's looking at what a variable is, some common variables in a lovely mnemonic that we have, line and bar graphs, potentially even a little bit of a pie chart, and then extracting information. So when we do an experiment, we know our aim is to find the effect of the thing we change on the thing we measure. The thing we change is our dependent variable. No, it's not. The thing we change is our independent variable. So this slide is incorrect. That's not very helpful. So the independent variable is the one that we change. So for example, on the right-hand side, we have hydrogen peroxide. We've got a lump of something, maybe a catalyst, and it's going to break down into water and oxygen, as our word equation at the bottom shows us here. So some variables here. What we've changed maybe in this experiment, we might be changing the temperature between different experimental groups. We might change the concentration of the solution between different groups. We might change the type of catalyst. There's lots of things we could change about that experimental setup to do this investigation, and these are all variables. So variables are things that you should either keep the same, change, or measure during the experiment. Some common variables: Mr. Collier thinks that the penguins vote. So mass, concentration, temperature, time, type, pH, and volume. So we can see here, this is, again, 20 degrees, 25 degrees, half a mole, a lump. This is probably some kind of solid that's reacting with an acid at different temperatures and different concentrations. So an important thing here is that a common question we would get asked is, which of these could be compared to find the effect of temperature on reaction rate, for example. An important thing is we have to make sure all of the variables are identical except for the one thing that we are changing. So if we want to find which of these are identical, boxes A, B, C, D, E, and F, which of them, say A and F, are identical except for their temperatures? So let's have a look. That was a good guess. So in A, we have a lump of whatever the solid is. We've got 0.5 mole per litre concentration acid, and it's going at 20 degrees. In F, we have a lump, same concentration, but the temperature is different. So if we ran 5 repeats of A, 5 repeats of F, and then we compared those, we could say F always goes quicker. We always have a higher rate than in A. That means that increasing temperature in this reaction will also increase the rate of reaction. If we, however, compared, let's say, D and F, they are at different temperatures. They have different concentrations, and one of them is powdered, so has small particle size. One of them is a lump. So if F is faster than D, we don't know if it's the temperature, the concentration, or the particle size. So you have to keep as many things the same as possible. So always when you're setting it up, think, have I kept the mass of the solid the same? The concentration and volume of any liquids the same? Is the temperature the same? Have I left it for the same amount of time? If a temperature change is what you're measuring, was the initial temperature the same? If not, we'll have to do a percentage change. Is the type of catalyst, is the type of chemical, is the type of acid, is the type of whatever being kept the same? And is the pH also kept constant? So if you struggle to remember these things in an exam, Mr. Collier thinks that the penguins vote. You can come up with whatever one you want for that. So section 3, we're looking at drawing line and bar graphs. So this one here, this would be a bar graph. So this, depending on which science you're doing, there's a number of marks available here. So usually the first column is our independent variable. It's the thing that is different. And then the second column is the y, is the dependent variable, is what we are measuring. So we have to make sure in this case, type of battery should be written below the x-axis here, because that is our label. And storage life in years, storage life / years, should be written on the left-hand side here. That usually gets you a mark. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 boxes, and we've got 1, 2, 3, 4, 5 different battery types. That would suggest to me that if I wrote alkaline here under these two boxes, I can then write zinc chloride onto the next two, silver oxide onto the next two, nickel cadmium onto the next ones, and the final two boxes could be lithium. So I can use 2 boxes per bar. If you want to leave gaps between the bars, which is absolutely fine, you could write alkaline under the first one, skip a box, write zinc chloride onto the next one, etc. So as long as you are keeping that consistent, that is okay. And you have to make sure that everything you write is kept underneath the one column. What we would then do on the other side is the highest number and the lowest number. So the highest number here is 10. How many boxes have we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's nice and easy. Each of these can be 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. A common mistake we see here is students saying, well, my lowest number is 2. So I'm just going to write 2, 5, 7, 10. And that doesn't make any sense. Each jump has to be the same. So the jump from here, where it's 0, to that first box, if that's 2, the next jump also has to be a jump of 2. So if it went 0 to 2, it'd have to go 2 to 4, 4 to 8, 8 to 10. That would be absolutely fine, but you wouldn't be using at least half your graph paper. We try and do that where possible. What you would then do is, after you do this, if you had alkaline here, you would go up 1, 2, 3, 4, 5, and you do a lovely ruler line across and down. I don't really think shading in is necessary. Certainly if you shade and you end up shading out the lines, I take the marks off you, by the way. So try not to do that. I can see the lines, so you don't need to shade them in. Well, the line graph is very similar. Time is the first column, first row, so it goes underneath here, making sure we've got time bracket seconds. On the y-axis, volume of carbon dioxide bracket centimeters cubed. That's our first mark. Similarly, this goes up to 70 in this 1, 2, 3, 4, 5, 6, 7, 8 boxes. So I'm going to go up in tens, and leave that last one fallow. So 10, 20, 30, 40, 50, 60, 70, 80. We just won't use that last bit. Volume of carbon dioxide, so it goes up to 37. I'm going to say probably 40 might be the number we're using. So 1, 2, 3, 4, 5, 6, 7, 8. So that would easily go up to 40. So it would go up in 5, 10, 15, 20, 25, 30, 35, 40. Because we've gone up in fives and 1, 2, 3, 4, 5, each big jump, the major grid line is 5, and each of these minor grid lines here, little boxes, is a jump of 1. We then go along to 0, up to 0, so basically we've gone nowhere, and we've put a circle or a cross. Our next number is 10, so we'd go along to 10, and we go up to 12, because that's the number that corresponds. So up to 10, 11, 12. We put a wee dot across there. You go along to 30, up to 29, and etc., etc. What we would then do is we would join the dots. We would only draw a line, in this case, if you were joining the dots, between the data points that we had. If we're doing a line of best fit, you would line your ruler up with your points and try and get it so it follows the line of your values. And if it can't go through all of them, you have roughly the same number of points or the same kind of amount of space above and below the line. So maybe 3 points here, 3 points there. That would be absolutely fine. But as many points on the line as you can. Okay, so it's the same as bar chart. Label, label, scale, scale. Find your points, but instead of doing boxes, we're doing crosses, and then line of best fit in them at the end. I put pie charts in just at the end because it's important. So pie charts they always add up to 100%. So it's of a full, how much is each particular segment taken up? So in this case, in percentage crude oil, it's made of naphthalenes, paraffins, aromatics, and asphalts. This has to add up to 100%. You can't just have a bit of the pie that doesn't exist. It's been eaten, potentially. So 50 plus 30 is 80, plus 15 is 95. I would suggest, I'm no mathematician, but if we take the 100 and minus 95, that will give us 5 that's left over. We then come across here, and one of these things seems to be taking up half of our pie chart. That's probably going to be your naphthalenes, and look at that, they've already put it in for us. So that's just a nice, easy one. The first 50% is naphthalenes. The next one, I would say that's over a quarter. So over a quarter of the next one is going to be something. The next biggest number is paraffins. So it's going to be paraffins. We'd write that on the line. The next biggest number is aromatics, which we'd write on the line. And then this one here. So it's important to be able to go forwards, but also to go backwards. If you were asked to turn this, if they'd given you all the numbers into a table, you'd think, well, what are these different things? What could I put them under in terms of an organizing heading? Oh, well, these are all types of hydrocarbons. I'll probably make that my heading. So you make that your heading, and then you put the different hydrocarbons in. You then put the percentages in and made sure all add up to 100. So these are the different things that you need to know for the test. They are the things that this goes through. Just have a go at your revision sheets, and if you've got any problems, you know where I am.